We now discuss the solution of a problem from the section Linear Algebra. The question is based on the concepts of diagonalizable matrices. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022 and it is from the part C. The given question is, let A be an n by n matrix. We say that A is diagonalizable if there exists a non-singular matrix P such that PA P inverse is a diagonal matrix. Which of the following conditions imply that A is diagonalizable? Option 1. There exists an integer k such that a power k is equal to identity. Option 2. There exists an integer k such that a power k is nilpotent. Option 3. A square is diagonalizable. Option 4. A has n linearly independent eigenvectors. We are given a matrix, an n by n matrix capital A, and we are given the well-known definition of the diagonalizability of a matrix. So when do you say a matrix is diagonalizable? If there exists a non-singular matrix P such that PA P inverse is a diagonal matrix. Now, which of the following conditions given below, that is in the options 1, 2, 3 and 4, imply A is diagonalizable? That means take this condition and say whether A is diagonalizable or not. That is our given question. We now discuss the solution of the problem in detail. We have capital A, an n by n complex matrix. And in this question, and over what field this question is based is not given. Therefore, we are taking that the field F as the field of complex numbers. And that is why we take A, an n by n complex matrix. Option 1. There exists a positive integer k such that a power k is equal to identity. Then A is diagonalizable. This implies A is diagonalizable. So, there exists a positive integer k such that a power k is equal to identity. This implies a power k minus I is equal to 0. This implies A satisfies the polynomial x to the power of k minus 1. Therefore, the minimal polynomial of this matrix A divides this polynomial x to the power of k minus 1. We note down that x to the power of k minus 1 is equal to 0 will give the kth roots of unity, and they are all distinct. What are the kth roots of unity? E power 2 pi I by k j, where j takes the values 0, 1, 2, 3, k minus 1. They will give you the kth roots of unity, and we know they are all distinct. Therefore, the roots of the minimal polynomial of A are also distinct. This implies the minimal polynomial of A is a product of distinct linear polynomials, and this will imply A is diagonalizable. This is a necessary and sufficient condition. That is, A is diagonalizable if and only if the minimal polynomial of A is a product of distinct linear polynomials. Agreed. So the option 1 will imply that A is diagonalizable. Move to the, therefore the option 1 is true. Move to the next option, option 2. There exists an integer k such that a power k is nilpotent, implies A is diagonalizable. Is it so? And this is not true. To substantiate that it is not true, we give a counter example. Let us take A is equal to the 2 by 2 matrix 0, 1, 0, 0. We have A square is the 2 by 2 0 matrix, and this A square is nilpotent. Yes. So that means for k, there is a k is equal to 2, A power k is nilpotent. This is nilpotent. Now note that A is A diagonalizable? Note that A is 0, 1, 0, 0 is a non-zero nilpotent matrix of index 2. We know that every non-zero nilpotent matrix is not diagonalizable. So A is a non-zero nilpotent matrix, and we know such matrices are not diagonalizable. So A is not diagonalizable. So the option 2 does not imply that A is diagonalizable. So the option 2 is not true. And the option 3, A square is diagonalizable, implies A is diagonalizable. Is it so? Now take the same example above. Let A is equal to 0, 1, 0, 0. A square is 0 matrix. Yeah, A square. And a 0 matrix, the 0 matrix is diagonalizable. So the A square is diagonalizable. But whereas A is not diagonalizable because it is a non-zero nilpotent matrix of index 2, and we know that every non-zero nilpotent matrix is not diagonalizable, and hence A is not diagonalizable as above. Thus the option 3 is not true. That means the option 3 does not imply A is diagonalizable. So option 2 is not true, option 3 is not true, and whereas option 1 we have already proved that it is true. Let's go to the, and it is worthwhile to remember the following result. What's the result? The only nilpotent diagonalizable matrix is the 0 matrix. The only nilpotent diagonalizable matrix, if a matrix is nilpotent and it is diagonalizable, then it is only the 0 matrix. The only nilpotent diagonalizable matrix is the 0 matrix. And we can also say that every non-zero nilpotent matrix is not diagonalizable. Agreed. We go to the last option. Option 4. A has n linearly independent eigenvectors, implies A is diagonalizable. This is a very well-known theorem. It is a necessary and sufficient condition for a matrix A to be diagonalizable. And it is true by the following diagonalization theorem. What is the diagonalization theorem? A square matrix of order n is diagonalizable if and only if A has n linearly independent eigenvectors. And if you have n linearly independent eigenvectors, and how to write down that matrix P such that PA, P inverse is diagonal matrix, and all that is well known. So a square matrix of order n is diagonalizable if and only if A has n linearly independent eigenvectors. Therefore the option 4 is true. Agreed. And we have proved the option 1 and option 4 are true, and option 2 and 3 are not true. So the answer to this question is option 1 and option 4. That is the detailed discussion of the solution of the problem on diagonalizable matrices from the section Linear Algebra. And I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.